I think E is a little bit harder not to see a function and its derivative, but it's hard to see when you look at this. Does this scream natural log to anyone? No, not at all, right? They're like, well, what do you mean natural log? Well, the reason is I look at it, I do notice I have a function and its derivative appear. So it makes me think I should make my u the x cubed minus 5x, and its derivative, du dx, would be 3x squared minus 5. So I could replace the 3x squared minus 5 dx, all of that can get replaced with the du, which would be in the top of my fraction, and my bottom of the fraction would just be a u, which I could write like this. I don't know, maybe I would sometimes. Maybe sometimes I would just think of it as 1 over u. I actually like that better. I'm going to take this out so you don't have to write it. And you can have it like this. Du over u, which is equal to 1 over u du, or u to the minus 1. But I see 1 over u reminds me of natural log better than u to the minus 1. But maybe you're better with u to the minus 1 compared to 1 over u. So does it make sense? The whole numerator with the dx would become du, and your whole denominator would become u. And then you get a 1 over u, which is a natural log. And I think that's what makes this one a little bit harder. It's not as easy to see when you looked at it directly that this would be a natural log question. But once you do the substitution, it appears. The 1 over u appears, and you know that that is the integral. Remember, if you try the product rule with a minus 1, if you add 1 to the exponent, you get 0, and then you have to divide by 0. That's like, should remind you, hey, something's going wrong here. That's my natural log function. Okay. A couple more. I mean, that one wasn't super hard because it was pretty easy to see the derivative. A couple more easy ones. E to the x is so easy, sometimes it makes it hard. Does that make sense? Because the derivative of e to the x is e to the x. But sometimes that makes it hard because it looks like nothing's changed. So again, where am I going to put my u? I would choose my u to be this 3e to the x. It really doesn't matter when I say let u equals. But that is inside of cos. So that causes a chain rule to happen. Then our derivative is still 3e to the x. And when we substitute, it becomes an easy integral. So the whole purpose of substitution is to take stuff that looks complicated because a chain rule would have happened and simplify it so that it's an easy integral. Is the integral of cos positive or negative sign? Positive sign. And then you can substitute back. So we need to know our derivatives really well so that when we see one, we can also see its derivative. So this is really, it sort of is a skill to be able to look at an equation and go, hey, I know the derivative of tan is secant squared x. So, and the tan is inside of another function, in this case sine. The question itself looks terrible. Sine, tan, wow. There's a whole bunch of trig functions happening here. But if we do that substitution then, u is tan, its derivative is secant squared, We can get du by itself, secant squared dx. Oh, this question is missing the dx. Is it missing it in yours, or did I fix it? Yours is good, okay. And then this simplifies nicely to sine u, which this time we need the negative. And you can substitute back. And again, anytime you're wondering what should you have done, you can always take the derivative afterwards and solve. And I've been waiting for H. But I'll let you catch up. Can you see I'm kind of starting to bubble with excitement? I like H. I like H because it's a little bit messed up. So, the derivative of sine is cos. The derivative of cos is negative sine. So what we pick is our u and our du. We actually have some choice here. We're going to do it two different ways. So I'm going to just start off with the easy one, which is making u sine x. I think this is the easiest one because the derivative of sine is positive cos. But the problem when I do the derivative here is I have a little chain rule. And we have in our question cos 2x dx. We don't have this extra 2. But we can deal with that by, see how I moved the dx to this side and I divided the other side by 2 to get the cos 2x dx by itself. Now I'm not replacing just du, I'm replacing du with a constant in front of it. And that 1/2 you could have there, you could have it in front because it's just a constant. This is an easy integral where you add 1 to the exponent and divide, which is just u squared plus c over 4. So what this question added is sometimes our derivative doesn't match perfectly. It just mostly matches. And if it mostly matches and is just missing a constant, substitution can still work. So notice the derivative of sine 2x is cos 2x times 2. But our original question didn't have the cos 2x times 2. But if the only thing that's different is a constant in front or multiplying by some coefficient, you can still rearrange to have it work. Now, I said I wanted to have fun with this. You don't have to write all of these down, but I'm going to do it again and say, let's say you made u the cos 2x. Okay? Then du dx, the derivative of cos is negative sine 2x, and we would have a chain rule times 2. And I could get du by itself by multiplying by dx, and then I could divide by the negative 2 so that I get the sine. There we go. That was perfect. I can get the sine 2x dx by itself. As far as going back to our original, now this purple box is going away, and now there's the purple. that would get replaced with negative 1/2 du. And the cos 2x gets replaced with u. So I have the integral of u times negative 1/2 du. Again, an easy integral, negative 1/2, add 1, divide, plus c. And I get negative. Now my u was cos 2x. Or did I write the squared? You okay if I write the squared in there instead of putting in big brackets? All divided by 4 plus c. Which is kind of crazy because this is also the right answer, but it doesn't equal the right answer. It's not the same answer as A, and they're not identities, which is a little messed up. So since we're messed up, we're going to mess up a little bit more, just for fun. Because this is the kind of creativity that's going to be sometimes needed in the questions moving forward. Do you know this? Is this one of the ones you've memorized? So my question is, do you see how close this matches to the right-hand side? What's missing? A 2 out in front. Now it's good, but I'm not allowed to do that, am I? Well, what happens if I do that and I do this? Then I'm okay. Because if I put a 2 and a half, that's really like putting a 1. If you don't like them that far apart, put them really close to each other. Are you okay with that now? And now all of this in the blue bracket matches this on the right-hand side, but instead of an x, I have a 2x. So if I wanted to, I could change this. The half would still be there, but now in this blue set of brackets, I would have sine 4x. And this is an integral you can do without substitution. Because the integral of sine is positive or negative cos? Negative cos, I have negative 1/2 cos 4x, and because it's a simple chain rule, where I would normally multiply by 4, I have to divide by 4 plus c. So a third answer to this question, which is not an identity to the other two, is this. Right? I mean, I don't recommend on your AP exam being like, you're stuck, just write down something and said, I figured this out by a method you can't figure out, haha, and hope they give you marks. Chances are they won't, if you haven't shown any of your work. But it is weird that we can get 3 different, completely different answers. Like if you graph them, if you graph all 3 of them, they don't match up. But somehow, this works. Yes?
If you were using it in a situation, how would you know which one to use then?
They're all right.
Like
So
they're not equivalent.
They're equivalent as far as the plus c goes. They're all right answers. And what makes it kind of neat is it would allow you, if it wasn't working in the idea that you thought, maybe there's another idea that works better. So I was excited about H. The next one I get excited about is L. So I'm going to tell you, well, I want to do this one together. Because it's another one where the derivative doesn't really show up. Okay? And it also is an important one to do because sometimes you cannot substitute enough and still have things match up. Okay, so a couple of things as far as getting skilled at this. Usually we're undoing a chain rule if we're using substitution, which means that there had to have been a function inside of another function. Right here, that's inside of e to the x. So is just the 4x squared, but you need to make your u the 4x squared plus 1. Now, what's the derivative of that inside function? It's 8x, but we don't have 8x, but we do have the x. So as long as you have the meat and potatoes of the derivative, like the important variable parts, the numbers in front and the coefficients you can manipulate with. So when I take the derivative of this, I get 8x. If I move the dx over, I can divide by 8 so that, here it is, oh, look at the purple box. That can, all that purple can get replaced with 1/8 du. I mean, I could have written it that way so the purple box was nicer, right? If I rearrange my equation, I can make the purple box fit nicer there. And then when we substitute in, we just have an extra 1/8. But coefficients, constants, don't affect our integration. That 1/8 stays there. Integral of e to the u is e to the u. So as long as the main part of the derivative is there, you're going to, coefficients you can work with. So is it okay with you, so you have more time to work, if we very quickly just show the answers for J and K? They'll be on the video. If you want to look at them later, you can. Don't need to write them down right now. Maybe you just want to try them on your own. But they're going to be very similar. Like, derivative of an x to the 4 is an x cubed. That matches up. Even though the numbers don't match up, we had to rearrange. Then, if we substitute in, everything works out nice. Again, this will be on the video. You're not going to have enough time to write it down. I know some of you are trying. Yeah, sorry. That way we can move a little bit quicker. Because if I see you trying, then I'll feel guilty, and then I'll wait. Same thing here. What's the derivative of a 4x cubed? They give me an x squared, but not a 5, but it doesn't matter. I can rearrange. I can multiply to get that 5x squared. Or I could just factor the 5 out in the front and leave it till later. There's other options to do. But then this is a natural log line. But what I really wanted to do in our last question for today is this weird substitution. Because I see the 4 plus x inside of the square root. But its derivative is 1. And outside of the square root is an x. It doesn't match with how we normally want to do it. But everything else I could think about doesn't work at all. It's terrible. So I'm really stuck. So I start and say, well, okay, I see it inside. What if I make the u 4 plus x? Then without even doing the derivative, I can play around with that equation. I can say, well, if u is equal to 4 plus x, then x is equal to u minus 4. I just took that same equation and rearranged it. That doesn't seem helpful, but it will be very helpful. Because if I did the derivative du dx, it's just du is dx. So as far as the purple box goes, the only thing that I can replace that is that. But my black and my green at the beginning allows me to substitute the 4 plus x for a u and the x for u minus 4. And initially, you might feel like this is just the same, like, great. This is just like rearranging the kind of the same way. How is this helpful? But it's actually very helpful. Because in the first one, because of the square root, I cannot distribute. I can't put the x to the 4 and to the x because it's not allowed with the square root. But if I change it this way, I could. I feel like that should be a different color. Let's go purple. Yeah. I can distribute it here. And if I distribute it there, I will get, this is u to the half, this will be u to the 3 halves minus 4 u to the half. And then they're all powers, and integration is easy. Because we just add 1 to the exponent and divide. My numbers are looking terrible there, I'm sorry. I will make them readable. I think you can see that's 3 over 2. And then when you add the exponent, you divide by that. I already simplified. Then you substitute back in, and wow, look at the original function. Another way you could play with it, if you did this, you could also rearrange, although I like this better. So if you want to try that, that would be fine as well. Oh, there is one more question. I'll leave example 4. I said this would be last one.